now in the second part, the goal is to sort of understand how the previous formulation extends to, well, theories that in principle we care a little bit more about, and not just the simple cubic scalar theory. In particular, what we'll do is extend it to pions and gluons. Okay, so as I hinted at the end of the previous part, this is going to be done by introducing a very simple deformation, which is like literally a kinematical shift that we call this delta deformation, which is built precisely in a way that preserves all the zeros and the splits that we encountered earlier. And what we'll find is for different values of this parameter delta, we will either get pions or gluons. Okay, so that's the goal. And I'll spend most of my talk just really explaining how this deformation gives us pions and gluons, so I won't be able to spend much time sort of emphasizing what are the sort of new features that we learn from being able to formulate the amplitudes in this way. So I decided that it's a good idea to start just by summarizing that part. So first of all, by construction, we have that all the zeros and the split factorizations that we found at the end of last lecture will automatically extend for pions and gluons. In particular, for the case of pions, these zeros will actually imply the Adler zero, which is the famous zero that we have for Goldstone bosons due to the shift symmetry. And then on top of that, it will derive us to sort of, the splits in particular allow us to derive sort of multi-soft limits for pion amplitude. So we know that when we send a single pion soft, then the amplitude vanishes, but as you start sending a bigger number of pions that are adjacent to each other, the result actually ends up being finite, and you get some sort of soft factors that are universal. Okay, so the zeros and the splits extend. In particular for gluons, we can phrase the zeros very simply in terms of the standard kinematics in gluon amplitudes of polarizations and momentum. Well, for the scalar case, we set some collections of pi's dot pj to 0. For gluons, these zeros get uplifted for further setting the sort of same collection of epsilon i's dot pj's and epsilon i's dot epsilon j. This is just to sort of mention how they're phrased in more standard language, because in a second I'll rephrase the gluon amplitude in a different way that won't make this so obvious. So this is one aspect of it. The other thing will be at loop level, we'll understand that, well, by sort of thinking of these amplitudes via the surface integrals, we will be able to define the integrands on these generalized kinematics, which correspond to the surface kinematics that I mentioned in the beginning, where I assign momentum to curves not via homology, but from something which is a little bit closer to homotopy, meaning that each curve on the surface has some kinematical variable, and I don't have to set it to 0, even if in momentum space it's 0. And this actually will be crucial to define what we call perfect integrands. And the reason why they're perfect is because they make a lot of the features that we see post-loop integration already manifest even before loop integration, so directly at the level of the integrand. For pions, we have an integrand that satisfies the Adler zero even before loop integration, and all the sort of multi-soft theorems that we derive at tree level generalize to all orders. For gluons, we find an integrand that has some generalized notion of gauge invariance directly at the level of the integrand, and also for which all the cuts can be interpreted as matching some gluing of lower point objects. Okay, so this is what I'll spend most of my time. And then the last point, which I actually didn't emphasize in the previous lecture, is that as a consequence, again, of the sort of surface integral picture and the u variables and so on, we have hints, or like this formulation gives us hints of directions in kinematic space for which we can go off to infinity, for which the amplitudes as well as the integrands actually vanish much faster than individual Feynman diagrams. So this is what we call kind of hidden UV behavior. We're sort of used to seeing these features, for example, in n equals 4 super Yang-Mills, and there the fact that things vanish faster for the whole sum rather than single diagrams at a time is due to asymmetry, which is dual conformal invariance, and is very important for us to be able to kind of determine the integrands recursively. Here, we will see that using this formulation, we'll find similar directions for just standard Yang-Mills theory, where there's no supersymmetry, that will more practically allow us to derive recursion relations for these integrands. So that's what I'll end. Okay, so let's start. So as promised, what I'm going to do is I'm going to start with the surface integral that I used to define these trace phi cubed amplitudes at low energies, and I'm going to ask, so let's shift all these kinematic invariance associated to the curves, this xij, by some linear deformation that I'm going to call delta ij. Okay, so this is literally a linear shift. And what I ask is, I want this linear shift to be such that all the zeros that I found earlier are still there for any value of this delta ij. Okay? So if you're familiar with, I told you that the zeros happen in the locus where the non-planar dot products are set to 0. So another way of phrasing this is asking some shift that preserves all the non-planar dot products. And as it turns out, there's a unique solution to this question, which tells us that this delta ij should be equal to plus delta if I and j are both even, minus delta if they're both odd, and 0 otherwise. Okay? So this is what we call this delta shift. And so if we plug this solution back in here and we do it at the level of the surface integral, we have exactly the sort of same function as before, but now because of this shift, we're going to have an extra factor of the product over all the u even evens over the product over all the u odd odds raised to the power of alpha prime delta. Right? This is just what we find by literally plugging this kinematical shift at the level of the integral. Okay, so this is my delta deformed integral. All the zeros and splits that I derived earlier will be satisfied by this object by construction. And of course, if alpha prime delta is equal to 0, then what I get at low energies is just trace phi cube theory. That's what we've been studying for the past hour and a half. Now what I'm going to claim is that if I take alpha prime delta to be any non-integer value, so in particular here, let's say it's between 0 and 1, then instead, at low energies, what I'm going to get is the nonlinear sigma model. And finally, in the limit where alpha prime delta is literally equal to 1, then I claim that at low energies, I get instead Yang-Mills theory. Okay? So this is the thing that I'm going to explain throughout the next hour and a half. Okay, so in particular, this connection turns out to be simpler for the case of the nonlinear sigma model, just for the fact that, since alpha prime delta can be anywhere in this region, in particular, I can pick the locus where alpha prime delta is much smaller than 1, in which case, I can take the full low energy limit of this integral where both alpha prime delta and alpha prime x are all much smaller than 1. And so in the field theory, in this region, I'm just going to get literally the trace phi cubed amplitude with this particular kinematical shift. Okay, that I defined over here. Right? So in this region, it's fine. So I'm going to focus on just studying what happens in this region, just because it's slightly simpler. So the claim is that if I start with my trace phi cubed amplitude that depends on delta now in this way, and I look at the limit where now I'm probing energies much smaller than delta, right, so all my kinematics are much smaller than delta, so this delta, you should think of it as some particular mass squares that now some of the propagators have. Some of them will have positive mass squared, others negative mass squared, which means some particles will be regular particles, others will be tachyons. But the claim is that now when I go to low energy, so that x's are much smaller than delta, I'm going to get the sort of NLSM at leading order in delta, I'm going to get the Pion amplitude. Okay, so this is what I'll try to show. But before that, let's just make a quick comment. This delta deformation is really only well defined when I'm dealing with an even point amplitude, because that's a situation where I have the same number of even indices as odd indices. Okay, so in general, I'll only be applying this delta shift for an even number of external particles, which here makes all the sense because we know that we only have Pion amplitudes for an even number of external particles. Okay, so here's the definition of the shift that I'm going to perform. So let's see this in practice. So if we start with the 4-point trace phi cubed amplitude, what this shift tells us is that we should shift x13 with minus delta and x24 with plus delta. Okay, so this is the S and the T channel are now both shifted. And so now if I expand, making both x's much smaller than delta, well, at leading order, I'm going to get 1 over delta and a minus 1 from this term and a plus 1 from this one, which cancels. So we have that the leading piece is just 0. But then the subleading part, which be 1 over delta squared, maybe with a minus sign, and then x13 plus x24. Okay, so this leading part is precisely the 4-point Pion amplitude, okay, S plus T. Okay, so this is a very small example, but it worked here, so that's okay. But now I'll give you an explanation for why it works in general. So in particular, at true level, Pion amplitudes are fully determined by the fact that they satisfy the sort of standard, like if the pole structure agrees, so if it factorizes correctly on poles, as well as it satisfies the Adler zero, then these two conditions actually turn out to uniquely fix that we're talking about pions. At loop level, the story is not so simple, but I won't discuss it here, but we can actually understand that this sort of shifted trace phi cube theory really comes from some spontaneously symmetry breaking pattern that explains why we're getting pions at low energies. If you want, this is just giving you some particular UV completion of the nonlinear sigma model. Certainly a very non-standard one, but that's all that it's doing. But so let's understand at true level why we're talking about pions. So the first thing is to see that we have the correct pole structure after we perform this shift. So maybe one of the most important features of pions is that we only have even point interactions, right? When we have the NLSM Lagrangian, there are only even point interactions. And so that means that we shouldn't have any poles corresponding to chords that divide our polygon into two odd gons. Right, because those would correspond to factorizations that would produce two lower odd point amplitudes that both vanish. And so you see that if we look at the chords in this polygon that divided into two lower ongons, those precisely correspond to the chords that are even or odd. Right? So for example, x15, which is an odd chord, divides the octagon into two different pentagons. So it will be a factorization channel where the amplitude should factor into two 5-point amplitudes, which we know is not a pole of the nonlinear sigma model. And so the fact that we have shifted these chords with these plus or minus delta, and then we look at the expansion as x is much smaller than delta, means that we don't have these poles exactly as we expect. So these guys are not allowed, and that's exactly what this delta shift is doing, is removing these singularities. On the other hand, the only sorts of poles that we will have in the final answer correspond to the guys that are not shifted, which are the case for which I and j are even odd or odd even. So for example, here would be chords such as like chord 1,4. As we can see, 1,4 precisely divides this octagon into a square and a hexagon, which are again two lower even point problems. So that's why these sorts of singularities are allowed. Okay, so far we understood that this shift at least removes the poles that are not there for the Pion amplitude, but that's clearly not enough. I mean, there were loads of things I could have done that would do this. But now the crucial point is that the crucial point now is to prove that this theory still has the Adler zero, so that it vanishes when I send each momentum soft. Okay, so and very nicely, this is now going to be a consequence of the zeros that we found in the previous part, for like the zeros that are already there for trace phi cubed. So I didn't tell you before, but in general, there's this very simple class of zeros, which corresponds to the case where I pick an index, so say 1, and I take all the dot products with this index that correspond to particles that are not adjacent to it. So for example, for this 8-point example, if I pick 1, I have the dot products with 3, 4, 5, 6, and 7, which are all the particles that are not adjacent to 1. Right? So I don't have the products with 2 and 8. Those two guys are adjacent to 1. And so the claim already for trace phi cube theory is that if I set all these dot products to 0, then the amplitude vanishes. This is part of one of these hidden zeros that I was describing earlier. Okay? So we know, so in particular, this 0 will be there for any value of delta by construction, because that's how I built this shift. So now the crucial realization is that this limit is very, very close to a soft limit, right? If I send P1 soft, all these guys should be 0, but on top of that, I should also set P1.P2 and P1.P8 to 0, because that's what it is rephrased in terms of these dot products. But now the important thing is that for the shifted amplitude, when I first go on this locus, it vanishes, and if I further set these two guys to 0, I'm not hitting any poles. Right? I mean, the function is completely regular as I set these two guys to 0, simply because we no longer have the collinear poles that we originally had in trace phi cube theory. So the fact that the amplitude vanished in this locus implies that if I further set these two guys to 0, it will still vanish. Okay, so this is the sense in which these zeros are actually more primitive, like they imply the Adler zero rather than the other way around. This also explains why trace phi cube theory doesn't have the Adler zero, right? The original theory, it vanishes in this locus, but of course if I further set P1 dot P2 to 0, then I'll hit the pole, so of course it won't still vanish. Now I need to be a little bit more careful about how I take the limit. Okay, so this is the sense. So
this upper configuration, is it a physical configuration with real momentum?
Oh, at 8 points, it probably won't be. We would need to think about it. Definitely at 6 points, it will still be. Or yes. Well, at 4 points, for example, it definitely is. It's just saying that you're just sending P1 dot P3 to 0. The amplitude will already vanish there without sending P1 dot P2 and every dot product with P1 to 0. That's the analog. Yeah, here I just made a slightly bigger example to emphasize the point. Okay, so of course in 4 dimensions is just that when you send a few of them to 0, you might impose a lot of other constraints, right? That's the thing that we would need to check more carefully, and I don't know out of the top of my head. Okay, so this is basically all that I'm going to say about pions, because as it turns out, the description of gluons has a few more moving parts that make it a little bit more interesting. But so there are a few things that I would like to say, though, is that so this was at tree level. We can understand it this way. If we do exactly the same thing at the level of the integrand, we find sort of an integrand for pions that has the sort of the Adler zero by the same reason, because the integrand will have these zeros, will also be manifest at the level of the integrand. We can derive the sort of multi-soft factors from splits and so on. Okay, so all these generalizes to all loop orders, one loop and beyond. The other thing maybe that I'd like to point out, just as a more practical perspective, is that, I mean, if you want to actually compute the pion amplitude, I mean, the pion has an infinite Lagrangian. In general, as you go to higher points, it's going to be more complicated. This turns out to be an extremely efficient way of getting the pion amplitude, just because you can get a trace phi cubed amplitude trivially, and then you just do these shift, and you series, and the leading order is the pion amplitude. Okay, so that's all I want to say about pions. Now let's proceed to this more interesting case, which is, so I'm claiming that when I make alpha prime delta be literally equal to 1, then at low energies I should be getting gluons. So in particular, when this deformation is literally equal to 1, at the level of the surface integral, what I have is just a product over u even over u odd, where now this exponent is literally just 1, right? That's just the limiting case of what I found there. So now the first thing you can ask is, okay, so you say you're describing gluons, but so far this amplitude again only depends on these dot products of this scalar momentum. And in principle, if I'm talking about a gluon amplitude, somewhere I should see the appearance of the polarizations. Okay? So as it turns out, this is what I'll explain for the rest of the talk. In the way in which this object contains the amplitude is via a scalar amplitude, which sort of describes a scattering of two n scalars. But these scalars are crucially coupled to gluons, such that I can actually access the gluon amplitude by extracting a bunch of residues from this object. In particular, if I start with the 8-point version of this integral, I can extract 4 residues, which correspond to sort of localizing this process in the case where the sort of pairs of scalars kind of merge together and produce a gluon, which will leave me, after all, with the sort of gluon 4-point amplitude. Okay? So this is what I'll explain, but the point is that starting from this object, I can take a set of residues in these chords, x13, x35, so all the odd chords that are adjacent to each other. When I look at them, and I take the residue at 0, so I localize on an inner n-gon, right? Then the claim is that this object is precisely going to give me the n-point gluon amplitude, okay? But the n-point gluon amplitude is still going to be represented in a slightly different way than what we're used to, because it's still going to be written in terms of these dot products of the scalar momentum given by the xij's. Right? So, in summary, what's happening is that because each gluon entering in this process is being produced by a pair of scalars, the polarization and the momentum of the gluons will now be functions of the momentum of the scalars that is producing them. And so we can read these explicitly, right? So if we look at a particular vertex, we have 1, 2, right? So this is momentum P1, this is momentum P2. Then just by momentum conservation, we have that the momentum of the gluon, right, is just going to be the sum of the momentum of the scalars, right, just by momentum conservation. And also, and now finally, I mean, we can read it off from the Feynman rule. We know that this vertex is going to be proportional to the coupling constant times the difference of the momentum. So we can say that the polarization of the gluon is the difference of the momentum of the scalars. That is really the only thing it could be, because this is the only independent vector that we have, right? I mean, we already have that the momentum is P1 plus P2, so the only thing the polarization could be is the difference. In particular, of course, the polarization is only determined up to a gauge transformation, so we have that the polarization of gluon 1 would be P1 minus P2 mu plus some gauge parameter, which kind of adds the sort of momentum of the gluon. Okay, of course, this gauge parameter should drop out of the answer. So this is just purely a kinematical map that allows me to trade off the sort of kinematical variables of gluons for those of like 2n scalars, right? So for each gluon, there's a pair of scalars. So this is what we call scalar scaffolding, right? So it's, and so far, for now, I mean, I'll get back to this integral, how this integral is getting this amplitude in a moment, but for now, think of it as purely a kinematical map, okay? So in principle, I can start with my standard endpoint gluon amplitude, which depends on the dot products of the gluon momentum, as well as the dot products of the momentum and the polarizations and the polarization dot products, and apply this map for each gluon, and write this function as a function of the dot products of the momentum of the scalars. Okay, so that's all that I'm doing here. So, and this is what I'm calling this sort of scalar scaffolding representation of the gluon amplitude. This.
A quick question.
Yes.
So you start out with this colored trace phi to the
Phi cubed, yes.
cube theory. So the color that you assume has to match the symmetry, the internal symmetry of the Young-Mills theory.
Yeah, so exactly. So like, yeah, but there you have some freedom, right? So if you do SUN for like for the color there, then you would have SUN
Okay.
for the
Now for the Pion, for the nonlinear sigma model.
Yes, that is a little bit more interesting. So if you literally want to interpret this as coming from some symmetry breaking pattern, I can tell you about it. It's a symmetry breaking pattern where SUN gets mapped down into SUK times. So it's not so like it's not so direct.
I see.
So yeah.
Okay. Thank you.
No problem. Yeah.
Yeah, maybe I just hear one comment that, as you said, the integrand for the Pion and the same thing for the Young-Mills will have the Atlas 0 or the gauge invariant, but it's very important to work in this surface kinematics.
Yes, that will be very important. Yes.
If you go back to the usual kinematics.
Everything, yeah, that's the sense in which I was saying here. These objects that satisfy this will rely on these surface kinematics, which I'll discuss explicitly for the gluons in a second. Okay, so now let's just stick to this particular map, which so far doesn't rely on anything else, and we can ask a few questions which are natural when we're talking about gluon amplitudes, namely, what does it mean for this expression written in this way to sort of reflect the fact that the amplitude is gauge invariant as well as linear in each polarization, right? This is some features that we know. So gauge invariance is this statement over here, that if I shift the polarization by something proportional to the momentum, nothing should happen. And linearity is just if I rescale the polarizations, I just get the rescaling factor times the amplitude, right? Anyway, so I'm not going to derive it explicitly, but just by asking what these properties translate to in terms of the xij's, we find a very simple answer, which is that, so if we're looking at just these features for gluon 1, so in this case, let me call, this would be my gluon 1, okay, so this one over here, then this linearity in the polarization kind of unsurprisingly turns into some statement on linearity on how my function depends on this even index 2, right? The only reason why I needed an extra momentum is because I'm talking about gluons, right? If I had a scalar, I mean, it's just characterized by the momentum. The fact that I have a gluon tells me that I have momentum and polarization. That's why I need two scalars. So this linearity is kind of reflected in some linearity statement in the variables x2j. But quite nicely, these two statements get packed together in the following way. So it tells me that this gluon amplitude has to be linear in the variables x2j, but in a particular way. So it's this linearity dependence should be made manifest, that I should be able to write it as differences between x2j and x1j, where the sort of coefficient of these differences is the derivative of the amplitude with respect to x2j. That's just the statement that it's linear in this variable, where we're summing over all the j's around the polygon. But similarly, by symmetry, there's nothing special about 1, right? I should also be able to write it as a difference between x2j minus x3j. Okay, so anyway, so this is what you learn just by trying to translate these statements into xij language. Okay, so this is what they are. But already this has a very interesting consequence, which is that when you recast the gluon amplitude in terms of these variables, it ends up having a completely locked form. So in the standard way, we're used to the fact that there are gauge redundancies, which means that there are different representations of the amplitude, which of course we can in the end identify them to be the same by using, well, the sort of momentum conservation or any other sorts of identities that just come from gauge invariance. But here, in this way, the answer has a completely unique form, and gauge invariance and multilinearity turn more into sort of symmetry statements, if you want, or like saying that for it to be gauge invariant in gluon 1, then you must be able to write your answer in this form. Okay? So this is like the sort of an important aspect, which is that the amplitude has a locked form. Okay? Just also, maybe I should make a comment already here, as it was mentioned earlier before. Here I am assuming that my gluons live in d dimensions, okay, so that there are no kind of constraints now at the level of these xij and x2j. Okay, so let me give you a concrete example to make this point manifest. So if you look at the 3-point vertex, in this case I would associate, I would describe it by the scattering of 6 scalars, right? And so I could get the sort of gluon amplitude. So here I'm just drawing it as a triangulation. I'm not yet connecting to that picture, but it's associated to a particular triangulation where I have each of the 2 pairs of scalars produces a gluon, and then I have this sort of gluon vertex, right? And now if I recast this 3-point vertex in terms of these xij's, what I find is that the 3-point gluon amplitude can be written as these in terms of the x as this quadratic function in the xij's. Okay, so this is just a relabeling, and I'm just using this example to make manifest this feature that I highlighted here, which is that if you write it in this way, maybe it's not obvious that it satisfies this feature, but you can reorganize this expression to show that, to make, for example, this first form manifest, that we have, can be written as x24 minus x14 times something, then x25 minus x15, where x15 is 0, because it's one of these scaffolding chords, which ensures that the gluon's on shell, times something, and x26 minus x16, which is also 0, because it's just a boundary curve. Anyway, you can play with this and see that exactly the same thing holds in the other direction, and that's just what gauge invariance means. Okay, so this is one thing we should know if we're just writing gluon amplitudes in this way. The other question we can ask is, how does a sort of standard spin sum rule translate into this language? Meaning, if I have a gluon amplitude and I go on a cut, as opposed to what happens in the scalar theory, I don't just get the product of the lower point amplitudes. Instead, I have a spin sum over the polarizations of this internal gluon that I've localized, right? So, for example, here in this point, here I am at, 8. So, for example, at 8 points, I'm always thinking of there being some sort of this, what we call scalar scaffolding, just to say that my scalars are also always sort of producing these gluons. But I can ask, what happens when I go on some particular cut, which is where I have some gluon, right? So in this case, it would literally be what happens if I factorize on the S channel. Right? Like, how does the spin sum translate into x's? And this also has a very simple answer. And so what we find is that we can interpret this cut as a sort of gluing of the 2 lower point surfaces that we get when we cut along this chord. But now, in each of these lower surfaces, we have that these guys are gluons. So if we want to phrase them in terms of our language, right, we should also think that these gluons are themselves scalar scaffolded. So it's the sort of lower point amplitudes that we find are the ones that have this extra index corresponding to the fact that we think of these gluon as being scalar scaffolded. Okay, so there's some dummy index x left, and also a similar thing for these right amplitudes. So this is, and then we can write this residue very similar to what we found here as a sum now over two sets of indices. So if I label the indices on this side little j and the indices on this right side capital J, then this will be a sum over little j, capital J, x little j, capital J, minus x1, capital J, minus x j5. And then times the derivative of the left function with respect to this little index. So that's telling me ultimately that I'm kind of doing the polarization sum on these guys. Anyway, times m right. Anyway, again, this is just a translation. I'm just telling you what it looks like and also giving you the sort of pictorial picture that goes nicely with it. I go on a cut, and the two lower point objects that I get are literally the two lower gluon amplitudes, where now this intermediate gluon should be thought of as also being scaffolded, so that I can fully rewrite the cut as operations and gluing on these two lower objects. Okay, so this is the idea. So far this was just a translation, and now what I want to tell you is explain how from this integral we will land on, we will understand that the function that we get precisely satisfies these two features, which is what tells us that we're talking about gluons. Yes?
So are we in 4 dimensions now, or
no? It's still
so d minus 2, and how many states?
We are tree level, so there's no d dependence. At one loop there will be. At tree level, the amplitudes don't have any. They don't depend on d.
Aren't there d minus 2 transverse states? And
well, the spin sum at tree level, the spin sum is just eta mu nu.
Okay.
Right? So you never see, when you contract eta mu nu with itself, which happens at one loop, then you have an explicit d dependence. But here you don't see any d. So that's what. Yeah, yes. So there's a generalization of this at one loop. Yes.
And is there a simple way to see from here that certain helicity amplitudes vanish, or?
Well, that is a more intricate question. For that, you really want to go back to 4 dimensions, right? So that's very important. So, yeah, that's a more, there you need to sort of find a way of doing that and then conclude that. But here, nothing will vanish precisely because we are in general dimensions.
But what is j being summed over here?
Yeah, j, as I was saying, sorry, these little j summed over the indices on the left surface,
okay,
and capital J summed over the indices on the right.
There's no explicit sum over anything in the middle. It's just the eta mu nu.
Yeah, the eta mu nu is kind of generating these curves that cross the surface, if you want. Okay. It's really being recasted in this way. This you can write. Oh, yes?
Sorry. So maybe I missed it. It's probably a naive question, but at that point you kind of assumed the fact that if this is a gluon amplitude, then it has to have gauge invariance and it must be multilinear in the polarization vectors, right?
Well, I didn't assume. Now, so if you want, this is what the object I defined, and then I stopped. I said, look, I have this mapping that turns a gluon amplitude and recasts in terms of the momentum of 2n scalars. And I said, okay, let's just look at what that means.
Yeah.
And then from here, I'm saying, if it is a gluon amplitude, then it will satisfy this.
Okay, and you check that this is the case in every case that you compute.
Oh, I'm going to prove you that now.
Okay.
I haven't done that. That's what I'm going to do. Exactly. So I'm just saying that there are two features that you should check, right? The first one is this one. That will tell you, this is the avatar of gauge invariance in this language. And the second one is that on the poles or the cuts, it does the correct thing. So this was just translation. Yes. Okay, so I won't have time to show this one explicitly, but I'm going to show this one now. Okay? And as it turns out, this is just a very simple consequence of sort of computing. So what we want to do is basically compute these residue, right? We want to start with this integral and go on a residue when one of these curves goes on shell, right? So that I kind of produce the gluon, right? So this is what we call the sort of extracting the scaffolding residue. And so to do that, so before I told you that to actually write an expression for this integral, find the parameterization of the u's in terms of the y's, you needed to start by picking a triangulation, right? This is one of the points of the last lecture. And so as it turns out, to extract these residues is particularly convenient to pick a triangulation that has this form, okay? Where basically mimics the fact that I have well, it's a triangulation that contains these chords, ultimately. That's all that we're doing. So if we pick a triangulation that contains these chords, then the dual fat graph, right, that defines the surface will look like this. That's all. And as it turns out, so I'm not specifying anything about what's happening in the middle. I'm just saying that I should have these chords. And automatically, just by doing this choice, what I find is that ratio of u even over u odd, sorry, that's here as well, that's deforming this factor, turns into 1 over the product over all the y's. Okay, so this is extremely simple. So this is telling me that to go from trace phi cube theory to gluons, all that I need to do is change my integration measure from a dy over y to dy over y squared. Okay, provided that I pick this triangulation, but that's a very minor point. So that now my integral looks like this. Okay, so this was the only thing that changed. Okay, and so now this is my new integral, and I want to extract the residue as x13 goes to 0, where x13 is this scaffolding chord. Okay, that chord over there. Okay, so to compute this residue, you need to know one more thing, which is that you can write the residue of the function as the residue of the form. So I can write this as an integral over the residue of this form, so where the dependence on y13, which is, if you want, the sort of y associated to this propagator. Okay, so this is the function just 1 over y13 times the product over all the u's, where some of them will have some dependence on y13, right? Others won't, but this is just schematic. I want to compute this residue at y13 equals 0. Okay? This is ultimately because of what I said before, that when I make a curve go to 0, the integral will develop a singularity in the region where the u goes to 0, and it turns out that this region is when the y goes to 0. So anyway, you need a little bit more to know this, but I'm just going to claim this, which is that you can prove that the residue of the function is equal to the residue of the form that you're integrating when the y13 goes to 0. So now you can ask, so if you want to extract this residue, then this means that you want to collect from this part the piece which is linear in y13, right? Because this is a 1 over y13 squared. So you want to collect the part which is linear in y13. So for that, you need to ask, what are the u's that have an explicit dependence in y13, right? Like you ask, what are the UCs that depend explicitly on y13? And well, from what we saw also previously, the way we build the u's in terms of the y's is via this matrix multiplication, where, so the u's that will depend on y13 are those that correspond to curves that pass through these roads, right? So in particular, if I represent my surface as I did here, then there are only 2 types of curve that pass through this edge 1, 3, right? So the u's that will have a dependence in y13, which is a variable that I associate to this road, are those for which when I draw the words, I pass through this road, right? So that when I do the matrix multiplication, I get a factor that depends on y13. Okay, so that is the idea. So now from this point, I get that when I take this residue, I'll get a contribution from the curves that are of the form 1j, as well as from those that are of the form 2j, that start at 2 and end somewhere, right? So this residue, I can write as sort of some sum over j. Well, when I take the derivative with respect to dy13 of this thing, I get the d log of u 2j dy13, and then there's a factor of x2j multiplying it. Sorry, maybe this is getting very far deep here. I'll move. And then I also get a similar factor for u1j. Okay, so I get 2 factors, right? This comes from both curves that depend on y13. Well, actually, let me write this down there. I think now it's getting confusing, because this is an important point, so I'm actually going to write it here. This is going to take 3 extra minutes, but I think it's worth it. So what I'm saying is just a simple point, which is just that I have, for my curves to depend on the variable associated to these roads, right? They need to pass through this road, and then they can do whatever. So I have the curves corresponding to 1j, say this is j, but I also have the one which is 2j. Right? So that's the factors that I have there. So on the residue, I'm going to get a sum over x2j d log. Anyway, I'm just repeating what is there. Right, so these are the things that depend, and then I have this the exactly same product over u's, but that's evaluated, everything is evaluated at y13 equals 0. I'm doing a Taylor expansion, right? So I'm just picking out the part from that product which is linear in y13, so I have those two prefactors, and then I evaluate everything at y13 equals to 0, okay? Which is equivalent to saying that I'm going on the locus where u13 is equal to 0. This is the equivalence. Okay, anyway, so far this doesn't seem exactly like that expression that I have there. I see that on the residue I am at least getting 2j and 1j, so it's getting to that form. But now the next thing that the last thing that you need to know is exactly this feature of the use of the subsurface in terms of the use of the surface, which I also described earlier, which is just the fact that if I consider this subsurface where I don't have these two other roads, right? Then I have the u of this curve that goes from 1 to j there, so what we would call before 1j, is exactly equal to the product over u1j times u2j, right? It's the two ways of extending this into the bigger graph. Right, so this tells me that the product of u1j and the u2j is actually independent of these y, because, I mean, it ends up being a curve on the smaller graph, okay? Anyway, so that ultimately just tells me that these two d logs are equal to minus each other. So that means that I can write this instead as x2j minus x1j times the d log, so I can factor out the d log of u2j over y13, and then kind of combine it with everything else, which is evaluated at y13 equals 0. Anyway, so in the end, the fact that we turned our form from a dy over y to a dy over y squared meant that when we go on these residues, we need to pick out the piece which is linear in the x's, and that together with the fact that we have some knowledge of what these d logs are from just the simple feature of what are the use of the surface, let us show that on the residue locus, we literally obtain an object that at least makes manifest this first form that I told you here. Okay? So that's...
Every time you need an n-gluon amplitude, you have to go to the 2n kinematics and take n residues after doing...
From the integral, I mean, I start with the 2n, and I need to take n residues. Yes, from here, yes. But taking these residues are extremely similar.
Shortcuts of summarizing the final answer and having done that.
Well, I mean, you can...
have the 2n variables anymore. They're only n.
Well, it's important that you have more variables because you're encoding both the momentum and the polarization.
But at the end of the day,
Yeah, you want to take these residues, but the ultimate thing...
Observations and momenta, and...
Well, but here you're doing that. You're getting a formula of just...
You have to do this each time. You can't summarize the results once and for all. And
You mean what the function looks like after all the scaffolding residues? Well, I mean, other than just translating what the function looks like from here to there, no. But the only point is that these residues are very fast to take. I mean, because it's just literally picking the linear part of a polynomial. There's nothing more than that. So the residues are actually really simple to extract. What is not easy is to extract the full low energy limit of these integrals because the form is no longer logarithmic. This part is extremely simple to do. So the leading singularities are also very fast. So you just keep taking residues and residues, and then you get the sort of leading singularities of Gluon amplitudes in this way. But anyway.
I'm a little confused. Why is it that these residues you're guaranteed to produce like the Gluon rather than another scalar?
Well, they're not guaranteed. You're just checking that that's what's happening.
Okay. So, because I mean, if I thought about this having like a six scalar integral and like traced by cube over the...
But this is not traced by cubed anymore because I've performed this shift. That's what this shift is doing for you. It changed the integration measure. I no longer have a dy over y. Crucially, I got this dy over y squared. It's very remarkable, though, that the only thing you had to do on your integral was change from a logarithmic form to a kind of well, dy over y squared form to conclude that now, after you've taken these residues, what you get at low energies is gluons rather than scalars. So that should not be obvious. I mean, that
But couldn't that have to do something with the fact that this is symmetric under the, I mean, the two scalars that you're combining to get the gluons,
see, what do you mean? They're symmetric, yes, but it's not clear that, I mean, that object is defining these at low energies, right?
right, but just to get, in terms of the group theory structure, right, since there's something, by definition, I guess it's symmetric under the exchange of the two scalars.
Sure, so yeah, I mean, for sure, I can exchange here the two scalars with no problem. But here we're always fixing the sort of color ordering. Well, I mean, it's definitely true that this part of recasting the gluon amplitude in terms of the momentum of the scalars, I can definitely do, and it's obvious. It's also obvious that I would need two scalars just because of like all the data that is necessary. It's not clear though that if you start with this string amplitude that describes like trace phi cubed at low energy and you perform these kinematic deformation, that you should get these scalar scaffolded gluons. I guess that's the point that I was saying. Actually, the gluon amplitude, so maybe the another way of saying this is that if you look at the gluon amplitude in string theory, it's this very, where you make explicit the dependence on the polarizations and the momentum is a very complicated integral that has a load of terms. It's like you need to pick out which precisely combine all the polarization factors. You can actually go from that expression to this one in a simple way at tree level. At one loop, these things are more general. Yes, Yar?
By the way, if this is a little bit...
Oh my God, it's 10 to 5. Go ahead.
Suppose that you do the delta is 1, but you don't do the scaffolding, and you just want to interpret it as the scalar amplitude. Is it clear?
Yeah, they have some other poles. They will have quartic interactions. These scalars have... Well, you can definitely interpret this theory, because you can, at tree level, you can think of this as having your gluon amplitude in string theory, where like you're scattering gluons, but then you're picking a particular choice of the polarizations of the gluons to be in some particular way. So then you get an effective theory, and you can...
But because if I don't do the scaffolding, I don't identify these kinematics, I just see some scalar amplitude, which is...
But you will eventually conclude by looking at its residues that you are exchanging gluons in the middle.
In the fundamental theory. Yeah.
In the fundamental theory, exactly.
The effective theory would be just some scalar theory.
Well, I'm just saying, you look at low energies, and this is going to describe some scalars that couple to each other in some way. So you'll have parts which are just interactions between scalars, but then there will have parts where also you have scalars interacting with gluons. So you're just inputting the external states, but there will be both scalars interacting with themselves as well as scalars interacting with...
What is this theory?
Oh, this theory is just a theory. These scalars that you're seeing are just gluons for which the polarizations were fixed in higher dimensions.
Okay, so that would be just the gluon.
Yeah, so exactly. It's the original gluons, but they became scalars in lower dimensions because you're fixing the polarizations in some way. This is what's happening, and that's how you can go from the standard bosonic string amplitude to this form in a particular way. Anyway, that is definitely a way to go, but without needing to know any of that, you can also understand that this object is describing gluons just by showing that all of the cuts kind of describe the, gauge invariance for the gluons, and also the actual gluon cuts agree with what a spin sum for a gluon would be.
Is there a story for how the 2n Chan-Payton factor disappears and the n Chan-Payton factor appears?
No, we're never analyzing what's happening. Yes, we're just looking at the actual thing that multiplies the Chan-Payton factors. Okay, so let me now at least finish by explaining how this story generalizes to one loop, because that's where I think some of the more interesting parts are. I'm very happy to give you the exact definition, Yara, of how to get this from a particular polarization configuration of the gluons in higher dimensions. It's very simple. So you can really understand these scalars as being just gluons in higher dimensions. So that's all. But maybe I'll do that at the end for the people that survive. Okay, so now I want to discuss what happens at the level of the loop integrand. And maybe to begin with, even though for this audience now, maybe it's a little bit irrelevant, but I think we're probably all familiar with the fact that, for gluons, when we try to define the loop integrand, naively, if we literally draw all the possible diagrams, we would run into contributions like this one. Sorry, where from here, because I'm dealing with a massless particle, I would literally have a 1 over 0, and similarly from 0, 1 over 0 from here, right? But of course, I mean, these guys contribute to what are called scaleless integrals that basically integrate to 0 after loop integration, right? So these are what we call scaleless contributions, and so we usually just throw them away. Also, they're divergent, so I mean that's the only way which we can do. So the fact that we can have this freedom to basically add and subtract scaleless integrals means that, of course, there's no unique integrand. This is something that we're familiar with, but in particular,
they're scaleless, and we have a dimensionless regulator like binreg.
Yes, exactly. Yeah. Well, this is.
If you regulate them with something with a mass.
Well, but in general, giving gluons a mass is a little bit problematic, right? I mean.
If you have a dimensionful UV regulator, that's alpha prime.
Well, yeah, but so yes, but I'm just talking about problems in field theory. I'm not saying anything yet. I'm just saying if you literally compute all the diagrams at one loop and try to define a purely field theory integrand for gluons, these are like scaleless integrals that you usually throw away, right, when you're defining your integrand. But the fact that you throw away these contributions sort of is intimately related with the fact that the object that you define doesn't have, it's not gauge invariant, and also doesn't factorize correctly on cuts, right? I mean, in general, when you go on a particular cut, you won't be able to match it with the gluing of lower point objects. And this last problem of the factorization can be kind of very well summarized by the fact that, while at tree level, we also have a rational function where all the cuts we can interpret as gluing of lower point objects. At one loop, we have one new sort of cut, which is a situation where we cut the sort of loop propagator open. And in this case, we would like to match this process with a tree level process, but where we've now glued the two adjacent particles, right?
Interruption.
Yes.
Please move your car by 5 o'clock, which is in 5 minutes, or it will be towed. If you're in the
Because they're
parking
closing
structure.
down that parking.
Yeah. And close the door and lights out when you leave, please.
Okay.
Okay. Anyway, so here this is what is called the forward limit, right? And since I'm gluing these two legs, they have to be they're evaluated at momentum L and minus L, which ultimately means that on this side, because in this full tree level object, there will be diagrams where these two guys meet, then this limit is just divergent, right? So this is what's called.
But you never really need to evaluate a one particle cut to get the whole answer.
What? You don't need to in general. No, you don't need to in general, but I'm just saying it, but in principle, at tree level, you can give meaning to all possible cuts, right? If you, at the level of the one loop integrand, naively, if you wanted to give meaning to these cuts, this is the object you should match to, right? Of course, as you're saying, this is not possible. So, I mean, we don't have a meaning to this cut exactly. I mean, in general, we care about unitarity cuts, which would not just be cutting a single propagator, but this is certainly a residue of my object, right? I mean, in theories like n equals 4, this is not a problem because when I do the spin sum over the supermultiplet here, this actually kills this divergence, and so all the cuts are meaningful. And that's why, in that case, we can very nicely reconstruct the integrand just by the knowledge of what happens in all the cuts. Okay? But so already here, it's obvious that the problem with this limit is the fact that we're evaluating the lower tree level amplitude in some restricted kinematical locus, right? Where we're forcing this momentum to be equal to minus L, right? Because we're gluing. So it's a purely kinematical obstruction, if you want. And so what I'll tell you to end is exactly how these sort of surface kinematics sort of solve these kinematic obstruction by basically generalizing sort of kinematics in a way that introduces more variables, but such that we can match these cut for completely general kinematics. So this is what's called, so now let me summarize. So the surface kinematics is going to be the case where I'm going to assign a variable or kinematical variable to each curve on the surface, even if they don't have any value in momentum space. So in particular, so let me just do, so I'm always now thinking of a gluon amplitude. So if I draw an n-gon, I always want to look at, sorry, 2 n-gon, I always look at the inner n-gon. And now at one loop, I can, for example, consider triangulations that will look like this, say, where this would correspond to some sort of tadpole. Anyway, doesn't matter. So this is some sort of tadpole triangulation. And in surface kinematics, I would say that the sort of variable that I associate to this curve, which is like the curve x11, is not equal to 0. So it's a curve on the surface, so I give it some name. Okay? Similarly, if I sort of consider the curves that correspond to the standard kind of external bubbles, so maybe let me do this one. Anyway, so here, this all gets a little bit more tricky to draw, but let's say that I have some curve that looks like that, then I triangulate it in this way. Anyway, this is another triangulation where I have my dual diagram would be the case where I have a bubble here that looks like that. So in this case, I have my standard curve, which is like this x51, this curve here is the one that I'm setting to 0, which ensures that the gluon's on shell. But then I also have this other curve over here that I would call x15, just to say that it goes through the left of the puncture. And in general, I let this guy be non-zero, just because there are different curves on the surface. Okay, so my integrand will depend on all of these variables. So I'll turn them back on and I'll leave them there. And this will be very important for me to have an object that will match with a tree-level object in generic kinematics, which doesn't have this problem of being divergent. So this is the general idea. And so to do this, you see, the only thing that I need to do is just exactly what I did before at tree level. So I start with the surface integral for trace pi cubed, which has a logarithmic form in the y's. Now where the surface is now the punctured disk, I take the product over the u's associated to the curves on the surface and with some exponents xc. But now all that I do to go from Yang-Mills to these scalar scaffolded gluons is just change this logarithmic form to a dy over y squared. Okay, this is literally what we just did at tree level. You do the same thing at one loop. And then if you still remember from the beginning, originally this product was infinite because it came from all the sort of self-intersecting curves that we had at one loop. And just like at trace pi cubed, we can do a truncation of this object where now we keep all the curves. So we have the sort of u labeled by the self-intersection. And we keep all the curves where q is smaller or equal than 1. Okay, so we can again take some deformation of the full string theory object to something which is much simpler that still defines Yang-Mills amplitudes at low energies. In particular, where we only have contributions from curves that self-intersect at most once around the puncture. So this is a finite product now. And on top of that, we saw that at loop level, we also had contributions coming from these closed curves that went around the puncture. And now, very importantly, this exponent of the closed curve, which so far I haven't told you what it is, and for gluons, this delta should be set to 1 minus d. So where d is now the space-time dimension. Okay, so this is how at one loop the integrands will depend explicitly on the dimensionality of space-time. So that is enclosed via the exponent that we associate to this closed curve. So the claim is that if we start with this object, assign these exponents according to the sort of homology rule rather than the standard, homotopy rule, like this one where I keep the variables associated to the curves that in momentum space have 0 momentum assigned to them, I have an object which is just defined by the low energy limit of this integral, and that's what I'm going to call the sort of surface gluon integrand, which is defined on surface kinematics, so on this generalized notion of kinematics. Okay, so now, just for an example, I mean, one thing that we will, yeah, okay, maybe another sorts of curves that these integrand will also depend on in like sort of things that are like these sort of boundary curves, which are literally things that usually are also set to 0. So it will have also dependence on these sort of variables. So these are the sort of new curves that are there that don't have any physical meaning in momentum space, but that are very important, meaning this curve doesn't have a physical meaning, it should be set to 0, these ones are all set to 0 as well, but the fact that we keep them there are going to be very important to have an object where all the cuts can be matched with lower point objects. Okay, so I think my time is running is ending because it's already 4. So I don't have time to kind of explain what the gauge invariance statements looks like or the cuts. I will just explain just by a picture for why at least I solved this problem that I pointed out over here. So the idea is that for this object, if I start with some loop level surface, when I go, that cut that I illustrated there, the loop cut, corresponds to taking the residue when one of these curves that ends on the puncture goes to 0. Okay, so in this case, when I cut my surface open via one of these curves, then what I should match should be the sort of surface where I've opened up this sort of loop, right? Like where I've opened it up into some sort of tree level surface, but where now these two guys, there should be a spin sum between these two guys, like exactly in the same way that it happened here, with the difference that I'm just, instead of opening the surface fully open, now I am opening it in this way, such that I get the sort of precisely this picture over here. I have a tree level surface where I'm now gluing the two adjacent gluons. Okay, so this is literally the picture. So these guys are gluons. Of course, in this picture of the scalar scaffolding, there will be also scalar scaffolded in some way, just like what happened here. But now you see, precisely because I allow in my original surface for there to for these variables to be non-zero, the tadpoles, on the tree level side, I will be matching with in generic kinematics. This is saying that at tree level, the curve corresponding to this particular channel, which precisely corresponds to the problem that I was illustrating there, where these two guys meet and give me and interact directly, precisely because I left the variable associated to this curve on the integrand, I'll be able to match these two objects in generic kinematics. Meaning, I guess what I want to say is that all the curves in this surface will map to a curve in this surface. That's really the point. Right? In the standard way, this curve in this tree level surface, when it gets mapped to the loop side, just has 0 momentum. So I'm in a divergent limit because I'm in restricted kinematics. And the same is true for all the remaining curves. So that's why I can have the precise mapping. Anyway, so this is the general feature, but the last point that I want to emphasize is the fact that provided I have an object where all the cuts can be interpreted as gluings of lower point objects, which is what's happening, the last thing that I need to know in order to be able to recursively construct it using this information is find certain directions for which my integrand vanishes at infinity. And so if I want to use some sort of Cauchy's theorem to reconstruct it, okay, so that is the last part which I mentioned in the beginning, which is this.
You get a divergence when you do the integral as you then go back into standard kinematics?
Well, if you can define the objects in this way, and then if you want to go back to standard kinematics, of course, you'll set these curves to 0, so you'll have a divergence. But you can, again, you can use this integral to you can use the recursion relation that I'll tell you about now to sort of recursively build this object. And then if you want to go to physical kinematics, all that you need to do is remove these terms that will give you. So you just have to map the curves that are mapped to 0 in kinematical space to 0 and remove those that give you divergences, and you can get back the sort of standard integrand that you would get when you throw away tadpoles and bubbles.
Okay, but
So,
the standard integrand will not have other 0 and will be non-gauge invariant. It's only in this surface.
yeah, the sort of fact that all the cuts match, also that there's a generalized notion of gauge invariance, and all that will go away when you do that. So that's why it's important to keep them there.
Because there is just no integrand in the kinematical space, which is gauge invariant or has other 0.
Yeah.
Anyway,
Only
so it seems like you have to keep track of all these small x11s and x1.
Yeah, you need to, definitely, your integrands will be.
Yeah.
Yeah, our integrands will be like much bigger.
I mean, one of the problems is the color ordering, because if you did it in color dress, that tadpole would be 0 by group.
Yes, it's like when you add all of them. Like, yes, that is also true. It's true. But here we're doing for each color ordering. Yes. But anyway, so let me just break this last point and then I'll end. I'm so sorry that I kept you for so long. So this last point that I want to mention is just because I think this is something that it's also true for these integrands and comes naturally as a consequence of these surface integrals, but that we again don't have a very good understanding. So, which is this sort of hidden behavior at infinity. So at tree level, from the surface integral, there's a set of directions in kinematic space that we can go off into, for which the whole amplitude vanishes faster than individual diagrams. And similarly, there's a very simple one that ends up being the case for the loop integrand, which is the case where I shift all these variables, these loop variables, that if this is this sort of xip, so the curves that end on the puncture, if I shift all of them by plus z, some parameter z, okay? As it turns out, the amplitude vanishes at infinity when I send z large. So this means that I can just use Cauchy's theorem to fully reconstruct my integrand just as a sum over these sorts of cuts, over the residues at xip equals 0 of these endpoint integrand evaluated at when all the xijp's. Anyway, this is just a standard Cauchy's theorem that tells me how I can just use the fact that I know what happens at each of these poles and sort of and also, anyway, this is just standard Cauchy's theorem in the function as a function of z. Right? I know that my function vanishes at infinity when z gets large, so then I can use the theorem to write as a sum over all the possible residues that I hit in z space, and those correspond to the different xips going to 0, right? When z is equal to minus the different xips. So that allows me to write my function as a sum over these residues over xip, so that means that I can build my integrand only by the knowledge of what happens on single cuts. Okay, and this is, again, something which is not possible in standard kinematic space because of all the reasons that I pointed out earlier. If you want, I mean, at true level, we were used to the fact that we had to slightly generalize kinematics to be able to be BCFW relations by saying that, already to define the 3-point amplitudes, we had to allow complex kinematics, because otherwise in real kinematics, everything would vanish. What I'm suggesting here is that if you want to do exactly the same thing at loop level, where you want to fully reconstruct the amplitude just by the knowledge of these single cuts, you need a further generalization of kinematics, where now the sort of kinematical variables are naturally associated to curves on surfaces. And that's what it's doing, and that's what gives us these integrands that have all of these nice features. Anyway, so this brings me to an end. Maybe just as a final comment, I hope over these last few hours you got an overall idea of what the word surfaceology these days stands for. I think within amplitudes, the things that we're kind of interested in understanding next is whether these sorts of formulation extend for uncolored theories, namely gravity. So whether you can think about gravity as a problem about closed curves on surfaces, as now those are the sort of natural variables that are associated to kinematics in uncolored amplitudes. That's one aspect of it. Purely inside string amplitudes, I think this new parameterization makes a lot of other features manifest, namely it allows us to derive different Regge limits, sort of recursive representation of the amplitudes, and so on. So this is another aspect of it. But overall, I think the sort of maybe the most important point that I wanted to transmit is how these ideas give us a very natural playground to sort of play with different theories, so not just trace phi cube theory, and understand how in this formulation there are certain surprises that are made obvious, both in the IR, maybe like the zeros and the split factorizations, as well as the UV, like sort of directions for which the amplitude vanishes much faster, or like faster than at least expected. So these are things that, we've seen features like these in theories where sometimes there's some sort of symmetry explanation behind these things, but in these cases, these seem to be completely, it's quite unclear why this is happening. In particular, it's happening for a set of theories where we wouldn't expect anything nice to happen. These are scalar theories. In the case of Yang-Mills, there's no supersymmetry, and still, his formulation gives us this kind of interesting, or hints into these interesting properties that I think definitely deserve a more deeper, or at least more standard understanding. They're obvious from this formulation, but not from any other, of course, not obviously in any standard way. And hopefully if we understand them, we might also be able to see if they're of any use for other problems in the context of particle physics. Anyway, so that's it. Thank you so much for those.